Hello everyone. On this video we will be just looking at a few more related rate examples. Okay, so once again you have to remember that these examples may not exactly match your, I guess you could say, your problems or your homework problems. These are more to reinforce a process or an approach more than just giving you a, okay, well, here's an example just like the one on the video, so go ahead and just copy down the steps. I want you to be able to figure out, because you have almost an infinite number of related rate examples that could pop up in front of you. I don't want to just teach you how to solve 3 or 4. I want you to have an approach to be able to solve any related rate problems that pop up in front of you. Okay, not just ones that look like these. All right. So hopefully you still have the steps written down from the previous video. So we're going to go ahead and solve this related rate problem here. Okay, so for this example, we want to find the rate of change of the distance between the origin and the moving point on the graph y equals x squared plus 1 if your rate of change of the x with respect to t is 2 centimeters per second. Okay, so if you have to write that down, feel free to press pause, but we're going to go ahead and start solving this one. Okay, so remember your first step. You want to identify your equations and sketch it. And for this one, a sketch will probably be a good idea. So identify equations and sketch. Okay, so once again, the sketch is not mandatory, but it does help you visualize. Okay, so if we sketch our y equals x squared plus 1, that's your origin, so y equals x squared plus 1 will look something like that. And that's assuming that this here is your 1. Alright, so this is your y equals x squared plus 1, which remember is just your x squared shifting 1 unit up. Alright, so let's say if your moving point on the graph, let's say it's about right here. Okay, so of course it's moving, so it's just not going to stay there. So this is your moving point. Okay, so we know it's going there, so we don't exactly know where it is at this moment, but we just have to be able to solve for it. So we're just almost like taking a screenshot from it moving back and forth to just right there. Okay, so we want to know the rate of change between the distance and the origin, so we already know that this is our origin. Alright, so what we're going to do is we're going to kind of eliminate the graph where all we're going to focus on is the moving point and the origin. Okay, so if we go without the graph, it will look something like this. You have your origin and your moving point would be right there. And again, that's your origin. Oops, let me kind of clean this up a little. Okay, now between your origin and that moving point, we're going to connect that, and we're going to call that our distance d. Okay, so you know at that moving point, you kind of draw an imaginary line straight down. Of course, it's going to be a right angle if you draw it straight down. This distance is your y, and this distance to that point is your x. Okay, so what we know is that we're looking for the rate of change of that distance if we know that your x is changing at a rate of 2 centimeters per second. So as this moves down, we know that this x value is changing at 2 centimeters per second. Okay, so we have our sketch. We have a general idea of where we're starting. So now we move on to our second step. In our second step, our primary equations. Okay, so we can see that from this one, the distance between the moving point and the origin, we can see once we created that right triangle, we're going to use the Pythagorean theorem. Okay, so that means, yeah, I guess you could say x squared plus y squared equals z squared, but in this case, x squared plus y squared equals d squared. So if we square root both sides, we end up with d equals the square root of x squared plus y squared. Okay, we don't have to worry about the plus or minus because we already know that distance has to be positive. So, all right, and what else do we know? Well, we know that y is equal to x squared plus 1. Okay, so we have our primary equations. Okay, now this part is the part that you really have to do a lot of thinking on because a lot of times it's not given to you. This is where you have to kind of go back to previous classes and figure out the equations like this one. Okay, so now you look at our third step. If necessary, we have to reduce it to one independent variable. Okay, so you notice here that your d, your distance, has two independent variables. It has an x variable and a y variable. We don't need both. We just need one. Okay, so what we're going to do is we're going to plug that y into here. So that means our d equals the square root of x squared plus y squared. Once we replace that y, that's going to give us our d is equal to the square root of x squared plus 1 squared. Okay, so we no longer have two variables. We replace that y, so that y squared becomes this squared. So now we just have an x variable. So once we make this x squared plus 1 times x squared plus 1, we go ahead and FOIL that out. And then we can combine those two. We end up with the square root of x to the 4th plus 3x squared plus 1. Or you can rewrite it as d equals x to the 4th plus 3x squared plus 1 to the 1/2 power. Okay, so now we have our one independent variable. Okay, and again with our fourth step, we don't really need it, but we're going to go ahead and do it anyway. That's our domain. Well, we need it, but we don't have to write it down. Okay, so we know that x is a real number. know that y is greater than 0, and we know that our d is greater than 0. Well, a real positive number. Okay, so now we use our fifth step to solve. Okay, so we see that our distance here. Now we want to find the rate of change of that distance. All right, so the rate of change of the distance with respect to time, because remember it's centimeters per second, so we're doing that with respect to time. And that's going to be the derivative of this here. So using the chain rule, we're going to bring down that 1/2 times x to the 4th plus 3x squared plus 1 minus 1, so that'll make that 1/2 minus 1 is negative 1/2 times the derivative of what's inside. So you have 4x to the 3rd plus, bring down that 2, we have 6x. Oh, actually using the chain rule, almost forgot a step. 4x to the 3rd times the derivative of what's inside of there, so that's times derivative of x with respect to t. Plus, we have our 6x here, times the derivative of what's inside of there, which is our dx dt. And the derivative of 1 is just 0, so we can kind of leave that out of there. All right, so now what we're going to do is we're going to factor out this dx dt. Okay, so rate of change of our distance with respect to t is going to equal, I'm going to put the 4x to the 3rd plus 6x, I'm going to put that right in our numerator. Because if we factor out our dx dt, we'll just make that dx dt. Okay, so we have 4x to the 3rd plus 6x. And that negative 1/2, so we know this goes in our denominator. So you have 1/2, or you just 2 in the denominator, times the square root of x to the 4th plus 3x squared plus 1. All right. Now we know that our dx dt is equal to 2. Now we didn't have to factor it out. We could have multiplied it by 2 in there, but I just went ahead and factored it out anyway. Okay, so we know that dx dt equals 2. So that's going to equal 4x to the 3rd plus 6x over 2 times the square root of x to the 4th plus 3x squared plus 1 times 2. Okay, where these two will cancel each other out. So that will equal, and I'll put this underneath here, 4x to the 3rd plus 6x over the square root of x to the 4th plus 3x squared plus 1. All right, so this way you could just pick any x value and plug it in to get your y value, And you can go from there. So once you plug in, well, you don't have to do it here because you got rid of the x value in your final answer. But once you pick an x value, you can just plug it in there and find out the rate of change of the distance. Right? So it's kind of giving you a general formula for this particular problem. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next example. All right, so for this example, and you've probably seen examples like this before, but we're going to go ahead and go through the steps. What if you have a man who is 6 feet tall, walks at a rate of 5 feet per second away from a light that is 15 feet above the ground. Okay. Now what we want to know is when he is 10 feet, I'll put the 10 feet from the base of the light, we want to know A, at what rate is the tip of his shadow moving, and B, at what rate is the length of his shadow changing. Go ahead and move that up. All right, so naturally we're going to start off by solving problem A. All right, so we're going to go through our first step. Doing that, we're going to identify our equations and sketch. I'll put identify and sketch. Again, sketching isn't mandatory, but it does a lot to help you visualize. And if you don't know what you're solving for, then you won't be able to solve it. That visualization helps a lot. All right, so now you get to marvel at my artistic skills. Okay, so let's say this is your light that is 15 feet off the ground, and of course we're assuming it's straight up, so it's a right angle. And that beam of light just kind of beams there, so we know that all that's covered in the light. Okay, so we know that that light is 15 feet above the ground, so we know that this is 15 feet. All right. So we also know that a man is 10 feet from the base of the lamp. So let's say we have a guy here. And we know that he is 10 feet from the base of the lamp. Well, when he is 10 feet, so right now, we're just going to call that X. Okay, and the reason we're doing that is because we want to find the rate of change while he's walking away. So that's why we're just going to leave that as X as his distance from the lamp base. Okay, which we're going to plug in later. Okay, so we know that, let's say right here represents the length of his shadow. Okay, so since we know that this is the distance from the base of the lamp, and this is the length of his shadow, then this entire distance, we'll call that L, which is the length from the base of the lamp to the tip of his shadow. Okay, so we know here we have our 6 foot tall man. Okay, so what do we also know about this X? Well, we know that if we have our, I'll put this right here, dx dt, that's the rate that he's walking away. We know that's he's walking away, but this is the rate of walking away. Let me make a little more room here. Rate of walking away from the lamp. Okay, so our little sketch gives us a little better idea. Okay, so now that we have a general idea of what we're doing, we're now just going to turn this into a regular, ordinary geometric shape. Okay, so we're not going to have all of the pictures and everything else. So we're going to redraw it. Oops, that's a little bit not as high as we need it. There we go. All right, so if we redraw it, again, this is the 15-foot lamp. This is the 6-foot tall man. This is the distance from the lamp, the base of the lamp. The length of his shadow, we'll call that M. It could be any variable you want. I just picked M. And the length from the base of the lamp to the tip of his shadow, remember that is L. Well, let me clean up this 6 a little bit. Okay, so now we have something a little more familiar that we can work with. We don't have all of this. Okay, so we were able to turn our question into our drawing, into an actual geometric shape that we can use. All right, so we're good on our first step. Okay, so our second step, we find our primary equations. Okay, so how do we find those? Once again, you have to go back to those old classes that you may or may not remember, or old formulas that you probably haven't seen in a while. Okay, so for this one, you have to remember similar triangles. Okay, so what's similar triangles? If you remember, if you don't, this will be a good little review for you, where if you have two triangles that are different sizes but have similar shapes. Let's say this is side W, this is side X, this is side Y, this is side Z. Similar shapes, but just one's bigger than the other. The ratio of side W to X is equal to the ratio of Y to Z. In other words, similar proportions. Okay, and that's what we're going to use here. We're going to have the big triangle with a similar proportion to the little triangle. Okay, so we see that before we do that, we see that L is equal to X plus M. So if we subtract X from both sides, that means that M is equal to L minus X. So we know our larger triangle, 15L, with the proportions 15 over L, is equal to our smaller triangle from 6 to M. Okay, so if we replace our M with L minus X, we have 6 over L minus X. Okay, so we're no longer using this one. I'll just draw a light line through it. We're using this one just because we replaced the M with L minus X. Now we cross multiply. So we have 15 times L minus X equals 6 times L. So we're going to go ahead and distribute that 15 because we don't need parentheses all over the place getting in our way. So we have 15L minus 15X equals 6L. All right, so if we subtract here, we have 9L equals 15X. So then we combine those two, then we go ahead and divide. So we end up with L equals 5 over 3X. Because remember that 9L, then we add the 15X. We divide both sides by 9. We have L equals 15 over 9X. Then we just simplify that. That's how we got our 5 over 3X. Okay. So forgive me, I kind of have a habit of skipping steps sometimes. I have to go back and show you how I came there. All right. So we're kind of running out of room. So we're going to continue this on the next page. But if you are still writing, by all means, feel free to press pause. But we're going to go ahead and move on to the next page. Okay, now we left off at L equals 5 over 3x. And actually, we don't need to do our third step because we already have one independent variable, which is our x. So we can kind of skip our third step. One independent variable. All right, so that third step really isn't necessary because we kind of took care of it just by having the x. Okay, and actually we can skip the fourth step because we don't really have to do the domain and everything else. So we can go right to the fifth step, which is solving. Okay, so we know that our L is 5 over 3x. Okay, so we go back to our original problem. Okay, we know our rate of change of x with respect to t is equal to 5. Because remember, I'm just going to put this right under here. He's walking at a rate of 5 feet per second away from the light. And remember, that's our dx dt. All right. And we also know that from the beginning, our x is equal to 10. Okay, we didn't plug that in at the very beginning because sometimes you'll have a problem that will say, what if he's 10 feet away? Then what if he's 15 feet away? This way you can just use this same formula over and over and over without having to do all that work again. Okay, so the rate of change of L with respect to our t is equal to 5 over 3. Remember, the derivative of 5 over 3x is just 5 over 3 times the derivative of what's inside times dx dt. Okay, we know our dx dt is equal to 5, so that's 5 over 3 times 5, which is 25 over 3. Okay, so our rate of change of L with respect to t is equal to 25 over 3 feet per second. Okay, so that tells us exactly the rate that the tip of his shadow is moving. Not him, but just the tip of his shadow. All right, so for B, we want to know the rate, the length of his shadow is changing. Okay, now if you remember, M is equal to the length of his shadow. And we know that M is equal to L minus X. Okay, so that means we want to know the rate of change of his shadow with respect to time. Excuse me. Okay, now we know with derivatives, you can rewrite this, the derivative with respect to time of the length of his shadow. But since we know that M is equal to our L minus X, derivative with respect to time of our L minus X. All right, so we know that from our properties, we can just kind of distribute that So this now becomes the rate of change of our L with respect to t minus the derivative of our x with respect to t. Okay, so we already solved for our derivative of L with respect to t. So that's 25 over 3 minus, we know that our dx dt is 5. Okay, so we can go ahead and subtract these. So we'll make this 15 over 3 just to get our like denominators. So 25 over 3 minus 15 over 3 will equal 10 over 3 feet per second. And that's the rate that the length of the shadow is changing as he's walking away. And now, of course, we know that that will change if he starts walking faster or slower, then our dx dt will change. But as long as he's keeping up this pace, then we know that, and of course, you know, he's 10 feet away, then we know that the rate of change, that's the rate of change that his shadow is changing for those two. If those two change, then of course this answer will change as well. All right. So hopefully this made sense, and I will see you on the next video.